Welcome back. So today we're going to talk about Big O. We're continuing talking about Big O. We've already talked about Big O of 1 and Big O of n, where we call this Big O of constant time, and Big O of n is, that is linear time. So linear time means that if you have an array with 1,000 things in it versus an array that has 10,000 things in it, Big O is that measure of how long something will take, and we're saying that the time an algorithm takes to complete scales according to how many things are in it. And in this case, it scales linearly, and in the O of 1, we say it doesn't matter how many things are in it, it's always going to take the same time. So today we're going to talk about Big O of n squared. So we're going to look at something that as the number of things you have grows, we're going to see that the time doesn't just take linear time. We're going to see that the time taken actually grows quadratically, or it's going to grow with a scale of O of n squared. So let's see. Big O n squared. What I'm going to do for this is I'm going to create a simple array list class. And we're going to have a constructor that starts with data being a new array of, say, 20 things. And it has a size of 0. And we're going to make a very simple method called append. And what append is going to do is it's going to take the data at the size and add the value. And then it's going to increment the size. Let's add another method here that says size, where we can just return this dot size. And let's make another method called remove at index, and this is a method which will take a for loop, and we're going to say let I equal the index that we're going to remove, and we'll say as long as I is less than this dot size, I++. And this is the same removal algorithm we did before. All that we're going to do is say this dot data at I equals this dot data at I plus 1. So shift values left to replace the index that was removed. And finally, we're going to say this dot data at this dot size minus 1. I just like explicitly setting that to null, and we'll say this dot size minus minus. So let's consider what the big O is of each of these functions. Well, the size function is a big O of 1, which is constant time. This function always takes a constant amount of time to run, no matter how many things are in the array. So this is a classic example of a constant time function. So although we might have added maybe 10,000 things in this array, we can see that this method, this function, is actually of O of 1 constant time, because we don't do anything except for just return the size. So the size gets incremented when we append things, the size gets decremented when we remove things, but this method itself does not depend on the size of the array. So however many times we call this method, it's actually always going to run generally fast. That's actually the same with the append. Now this append method, think for a moment, what is the big O of this method? Well, even though we're appending something, we always append it directly to the end of the array. So with this version of append, we don't have to shift things around. The other version of something to add to an array would have been like when we add it in the middle of an index and it has to shift everything over to make room. But since we only add to the end of the array, this is also an O of 1 constant time. For the same reason above, it always adds just to the end of the array. It always takes the same constant amount of time to append just to the end of the array. So, what we can see here is, now let's consider the remove at index. So think for a moment, what is the big O of this function? So this function, we have a for loop, and the for loop actually runs according to the index, and it depends on the size of the array. So this function actually is going to take time with a big O measurement of big O of n, which we call linear time. And this function will take more time directly proportional to the amount of items in the array. So we can see that unlike the size method and unlike the append method, with which both always took a constant amount of time, the remove at index is going to execute the for loop, and that for loop depends on the size of the array. So we say that this is linear time. So now let's write another function. I want to write a function which is called contains duplicates. And this function is going to return true or false depending on if there's any duplicate value in the array. So first of all, we have a question of, well, how the heck can we do this? I'm going to suggest that we can use two for loops that are nested inside of each other, and we can look for every single number in the first loop and go through the entire array to see if that number occurs anywhere else in the rest of the array. So let's code this up. Let's let I equal 0 and go while I is less than this dot size, and we will always increment it. And let's make another loop for j. And now we'll say if I does not equal j and this dot data at I equals this dot data at j, two identical values appear at different positions in the array. Here we can say true. And if both of those for loops finish without any sort of duplicates being found, we can return false. So this function is actually an example of something that has a big O of n squared, which we call, let's see, quadratic time. this function will take longer with a ratio of n to the squared amount of time per n items in the array. So what we can see is if this array only had one thing in it, it would finish rather immediately because it only has to check essentially one thing. And if the array had 10 things in it, well, what's going to happen is the first for loop goes from 0 to 10, and the second for loop also goes from 0 to 10, but this for loop is nested inside that first one, so this function is actually going to take a lot more time. So let's test this.